I'm going to talk about absolute convergence. And this is going to be important for us because it'll enable us to examine additional types of series that we couldn't do before. Recall for the direct comparison test and the limit comparison test. If we're studying something like the sum as k goes from 1 to infinity of a sub k, to apply those tests, we needed that we had non-negative terms, right? A sub k is greater than or equal to 0. And then in the case of the alternating series test, we focused on the absolute values, but originally we defined it this way. We had some kind of a sign flasher, negative k, negative 1 to the k, or negative 1 to the k plus 1. And again, here, a sub k had to be greater than or equal to 0, but this kept alternating between negative 1, positive 1, negative 1, positive 1, negative 1, positive 1. Well, what about something like this? Sum as k goes from 1 to infinity of sine k over k squared. So it is not always positive because sine is negative sometimes. And it's not alternating. It's not like it alternates from negative 1 to positive 1, negative 1 to positive 1. So the question is, does this converge or not? Does this converge, and how can we prove it if it does? That's what we need to think about. So we can jump to Wolfram alpha to get a feel if we think it converges or not. And then we can go from there to see, maybe I'll change it to, no, that's fine. That'll work. So let's go ahead and take a look at whether or not that thing converges. So let's take a look. We're saying the sum of sine k over k squared as k goes from 1, let's try 1,000 first. And let's see if we see a number here. So this is the partial sum up to 1,000. Up to 10,000, what do we get? 1.0139. Add another 0, does that make a difference? It's certainly taking a while to compute it. And maybe we have gone beyond Wolfram alpha's abilities. So indeed, 100,000 was too much for Wolfram alpha, but I went to 20,000, and again, we have about 1.01395. So it appears as if this thing is converging. But how can we prove that? None of our tests work. Well, the idea is that if we can show that the absolute value converges, then the original function converges. So this is a nice fact. If the sum as k goes from 1 to infinity of the absolute value of a sub k converges, then the sum as k goes from 1 to infinity of a sub k converges. So we can prove that. So let's look at this same sine k over k squared example. Sum as k goes from 1 to infinity, sine k over k squared. So a sub k is sine k over k squared. So the absolute value of a sub k is the absolute value of sine k over k squared. Now, I want to appeal to the direct comparison test. So let me ask you this question. What sequence should I compare the absolute value of a sub k to? So I want that to be either less than something that converges or greater than something that diverges. So think about what that will be. What should we compare that to? The answer is, well, we know that the absolute value of sine k is less than or equal to 1. So the absolute value of sine k over the absolute value of k squared is less than or equal to 1 over k squared. Well, what do we know about that one? The sum of 1 over k squared as k goes from 1 to infinity converges by the p-series test. Now, we are smaller than something convergent and, of course, bigger than 0. Everything obviously is positive there. So what do we conclude? We conclude that the sum of absolute value sine k over absolute k squared converges by what? By the direct comparison test. Or we could write it this way, right? Absolute value sine k over k squared converges. But if the absolute values converge, then we can use our fact. If the sum of the absolute values converge, then the sum of the original sequence converges. So conclusion, we say the sum of sine k over k squared converges. And why is that why? Because absolute convergence implies convergence. So that's a strategy that we're going to use often. So let's look at some of our favorite functions, and let's ask if they are absolutely convergent. So this time we'll make them alternating. So what if I have the sum as k goes from 1 to infinity of negative 1 to the k times 1 over k? My question here is this absolutely convergent? So what do you think? If we take the absolute value, which is going to eliminate the sign flasher, does the resulting thing converge? Well, a sub k is negative 1 to the k times 1 over k. So the absolute value of a sub k loses the sign flasher, just becomes 1 over k. So test for absolute convergence. See if it's absolutely convergent. Test for absolute convergence. We look at the sum of the absolute value of the a sub k, which is the sum of 1 over k. What does that do? That diverges. Why does it diverge? Well, it's the harmonic series is our reason. If you want to say it's a p series with p equals 1, I could live with that too. But the harmonic series is probably our favorite diverging series. So it is not absolutely convergent. But remember, the sum as k goes from 1 to infinity of negative 1 to the k times 1 over k does converge thanks to the alternating series test. So just because this version converges with the sign flasher does not mean that its absolute value does. So if the original thing converges, but its absolute value does not, in this case, we claim that it is conditionally convergent. So that term, the sum as k goes from 1 to infinity of negative 1 to the k times 1 over k, that converges, but not absolutely, is said to be conditionally convergent. So let's look at another one. and ask ourselves if it is absolutely convergent. Again, looking at one that is alternating. So if I have the sum as k goes from 1 to infinity, -1 to the k times 2 over k root k. So that's my a sub k. It alternates. Now, let me ask you this question. Would this converge with the alternating series test? If we did the alternating series test, would this converge? But I'm not going to do that. Instead, I'm going to look at the absolute value of a sub k and ask myself if the sum of the absolute values would converge. I'm going to look at that instead. The absolute value of a sub k is 2 over k root k. So the question I want to ask now is, does the sum of the absolute value of a sub k converge? Well, that's the sum of 2 over k root k, which is 2 times the sum of 1 over k root k, which is 2 times the sum of 1 over k to the first times k to the 1/2, which is what, k to the 3/2. And then what do we know? The sum of 1 over k to the 3/2 converges by the p-series test. We always want to compare to p-series if we can. 3/2 is greater than 1. P is greater than 1. So 2 times it must also converge. Yes. So 2 times the sum of 1 over k to the 3/2, which equals the sum of 2 over k to the 3/2, converges. And why is that? A multiple of a convergent has to be convergent. So indeed, we have shown that the absolute values converge, but then what do we conclude? If the absolute values converge, right? So putting all this together, we say the sum of the absolute value of a sub k converges, implies that the sum of the a sub k converges. So my conclusion then, without using the alternating series test, my conclusion is the sum as k goes from 1 to infinity of -1 to the k times 2 over k root k also converges. So it converged and its absolute value converged. So what do we call that case? When the original function converges and its absolute value converges, excuse me, the original series converges and the absolute value converges. What do we say? If the sum of the a sub k converges, well, that's going to happen. If the sum of the absolute value a sub k converges, then we say the sum of a sub k is absolutely convergent. Remember, absolute convergence implies convergence. So let me ask you to check with technology. So let's do both of them. First, using technology, let's show that this converges. Sum as k goes from 1 to infinity of -1 to the k times 2 over k root k. Please get an approximation for that using technology. See what that's going to be. So we go ahead and pull up Wolfram alpha. So we have sum of -1 over k times 2 over k times the square root of k as k goes from 1 to 100. Let's see what we get from 1 to 100. Apparently I had some kind of a typo there. Maybe I'm missing a parentheses. So -1.529. How about 1 to 1,000? -1.53. 1 to 10,000. And again, eventually we might give Wolfram alpha means a little bit too big for it to evaluate. And it looks like that might have happened here. So we get about negative 1.53. So this seems to be stabilizing in that direction. All right, now let me ask you another question. So we think this is about negative 1.53. So that does converge, which is nice, but we also said it was absolutely convergent. So to check for absolute convergence, let's try this, please. Use technology to get an approximation for this. Sum as k goes from 1 to infinity of 2 over k root k. What do you think that is going to be? So all I have to do on Wolfram alpha is to remove the negative 1 to the k. And let's see what we get. Let's do 1 to 100 first. See if it's stabilizing. 4.825, 1 to 1,000, 5.098. Okay. Is 10,000 going to be all right? 5.18. Let's go to 20,000. 5.18. We get a 20,000. 5.19. What, 40,000 maybe? We'll go ahead and we'll call it about 5.2. Sure, let's try 100,000. Let's see if that's going to work for us. Indeed, around 5.2, we'll say. So we can see here that these numbers are not the same. Certainly, this alternates. This goes negative, positive, negative, positive, negative, positive, negative, positive. If these guys are all going to stabilize, making some positive and some negative, there's no way that's going to go to infinity. There's no way that's going to bounce between two numbers. So if you are absolutely convergent, you will be convergent. So indeed, in this case, this is absolutely convergent. So let me ask you to do the following. I'll give you another alternating series. Okay, goes from 1 to infinity. Negative 1 to the k plus 1 of what? 1 over the cube root of k. So your choices are here. Is this divergent? Is this absolutely convergent? Or is this conditionally convergent? Those are your three choices. Divergent, absolutely convergent, or conditionally convergent. Make your choice. What are we going to say there? Well, first, let's see if it converges. We could certainly answer that question. What do we have? We have the sum as k goes from 1 to infinity. Negative 1 to the k plus 1 over 1 over the cube root of k. So if I just say this, if I say a sub k is negative 1 to the k plus 1 times 1 over the cube root of k, I can appeal to the what? To the alternating series test. Use alternating series test. So the absolute value of a sub k is 1 over the cube root of k. If you like, you could recognize that the absolute value of a sub k plus 1 is 1 over the cube root of k plus 1. If the denominator is bigger, the fraction is smaller. So the absolute value of a sub k plus 1 is less than the absolute value of a sub k, which implies that this thing is decreasing. And the limit as k goes to infinity of the absolute value of a sub k is the limit as k goes to infinity of 1 over the cube root of k, which is 0. So it decreases to 0. So in that situation, it alternates because of the sign flipper. It alternates, and the absolute value of a sub k decreases to 0. Therefore, the sum of a sub k converges by the alternating series test. sum as k goes from 1 to infinity, negative 1 to the k plus 1 times 1 over the cube root of k converges by AST. Now, is it absolutely convergent? So let's take a look. What do we have? That's our next question. Is this absolutely convergent? So what do you think? Yes or no? What do you think? So I've got the sum. As k goes from 1 to infinity, negative 1 to the k plus 1 times 1 over the cube root of k. So that's the absolute value of it. Excuse me, that's a sub k is this. Negative 1 to the k plus 1 times 1 over the cube root of k. What is the absolute value of a sub k? That's just 1 over the cube root of k, which is 1 over k to the 1/3. Look at the sum of the absolute value of a sub k, which is the sum of 1 over k to the 1/3, which diverges by the p-series test. So what's my conclusion? Conclusion, that is not absolutely convergent. The sum as k goes from 1 to infinity of negative 1 to the k plus 1 times 1 over cube root of k is not absolutely convergent. It is conditionally convergent. Let's examine the following. Let's look at the sum as k goes from 1 to infinity, negative 1 to the k plus 1 times k plus 1 over k squared. The question I will ask you, is this absolutely convergent? Conditionally convergent? Or divergent? Which one is it? Which one is it? All right, well, first of all, I want to see if it is convergent. So I'm going to first appeal to the alternating series test. So right now we have a sub k is negative 1 to the k plus 1. It's k plus 1 over k squared. The absolute value of a sub k is what? I lose the sign flasher, so what is it? It's k plus 1 over k squared, which is k over k squared plus 1 over k squared, which is 1 over k plus 1 over k squared. So now what do I get? Now what do I get? I get the sum of the absolute value of a sub k is the sum of 1 over k plus 1 over k squared. But can this converge? Can this converge? Cannot. Sum of 1 over k diverges. So this thing is divergent. Now, is it absolutely convergent? That's my next question. So how about the sum as k goes from 1 to infinity, negative 1 to the k plus 1, times k plus 1 over k squared. Is it absolutely convergent? The absolute value of a sub k is k plus 1 over k squared. Well, we already showed that, didn't we? Sum of the absolute value of a sub k diverges. We saw that on the previous page. So indeed, this is not absolutely convergent. It is not conditionally convergent. It is divergent. So just because it alternates doesn't mean it has to be absolutely convergent or absolutely convergent.